So now we're going to look at the most common method for evaluating limits, and this is just involving direct substitution. This is generally the first and the easiest technique that you will want to attempt on a given problem. So whether the directions for a specific problem mention substitution or not, you should always try just seeing what happens if you plug the given number into the function and see if you can simplify it. Now, the problem is a lot of times we use limits because you can't plug a number in directly, so there will be situations where that won't work. If you end up in a situation where plugging in the number is undefined, then my note down here is mentioning that you will have to do some sort of factoring or simplifying, find some way to manipulate and simplify the expression, and then you can try to perform the substitution instead. So here's a fairly straightforward example. I know it looks like it has a lot of ugly expressions in it, but once you actually try substituting 0 in for x, you're going to find that this is actually not too bad of a problem. So if I try to replace all the x's with zeros, I end up with e to the 0 power times cosine of 0. If you do not remember what the value e represents, it's a number like pi. It's irrational. It goes on forever and ever and ever. It's used for a lot of interest calculations, and it's a number that's approximately 2.7. So replacing the x's with zeros has given me a new statement that I can now simplify because any number to the 0 power, including an ugly decimal like 2.7 to the 0 power, is equal to 1. And cosine of 0, whether this is degrees or radians, it doesn't need to be specified because it's the same answer either way. So 0 degrees or 0 radians is straight to the right on the unit circle, which means the value for this is equal to 1. And then 1 times 1 is 1. So we're done. That's it. That's the answer. So this is usually what you should try first. Just take the given x value, the number that x is approaching for the limit, and just try plugging that in, because many times there will not be any problem with replacing x with the number. Here's another example that may seem difficult because there are some expressions we haven't used in a while in there, like natural logs. But again, let's just try replacing the x's with pi and see what happens, because this is saying what happens when x gets really close to pi. So let's test and evaluate natural log of pi over cosine of pi. Now, in the directions, I didn't specify whether I wanted a decimal or an exact answer, so make sure you're comfortable evaluating this either way. But many of the questions on your assignment will prefer that you keep it as the exact answer, which means we don't want to type things in as a decimal into the calculator. We want to try and do this without the calculator. So we're going to try to leave things in terms of natural logs and square roots, etc. So natural log of pi, that's not a number I'm expecting you to evaluate. I just want you to leave that as natural log of pi. If you want a decimal answer, then just plug it into the calculator. And cosine of pi, this is something you can do on the unit circle. This value is equal to -1. But instead of writing natural log of pi divided by -1, usually we would just say that this answer is negative natural log of pi. You can pull that negative out front, or you can write it on the top. Either way, it should come out the same way. So if I want an exact answer, then that's it. There was no reason not to just plug in pi. If it had been sine in the denominator, that would have been a problem, because then plugging in pi in the denominator would have given me 0 in the bottom of the fraction, and that would be undefined. So that's what we're going to look at next. What happens when you get an undefined value when you try to plug in the x number? So here's our last example for substitution, and I can already see that right off the bat, I'm not going to be able to plug in the number directly. We can't plug in 1, because in the denominator, that would give me 1 minus 1, which is 0. So direct substitution will not work on this one, which is why I have that note back here on the earlier slide. If the function is undefined when you plug in that x value, then you're going to have to do some factoring or simplifying before you can do the substitution instead. So going back to this problem, I don't see any factoring that can be done in the denominator, but in the numerator, we have a trinomial. So using our factoring techniques, I should be able to find two binomials, and I need the first numbers to multiply together to give me x squared, so it has to be x times x. I need the last numbers to multiply together to give me a -2, but I need them to add up to a +1. So it has to be a +2 and a -1. The order I do that in doesn't really matter. I could have flipped that and it would still be the same. So now that I've factored the numerator, it actually came out rather conveniently because I have an x minus 1 on top and an x minus 1 factor in the bottom. So since these two things are being multiplied on top, I can cancel that with that. You can't do it when there's like a plus or a minus sign in between the numbers you're canceling. So since those two terms cancel out, now I'm left with just the expression x plus 2. And so I still haven't taken the limit yet, so I'm going to keep writing off to the side the limit as x approaches 1. We want to keep writing that until we actually perform the substitution. So here's the step where I'm actually going to perform the substitution. I'm now going to replace x with 1, so I can write 1 plus 2, and that final answer is going to equal 3. So this is one of the kinds of questions where if we were looking at the graph, I wouldn't be able to just look at what happens when x equals 1 because there would be like a hole or something weird happening on the graph. But I could use the limit and look at the numbers really close to 1, like 0.999999, and that would lead me to believe that the answer was going to be 3. So that's it for our examples of limits. Again, just try to plug the number in directly. You may have to go back and refresh yourself on some of the factoring techniques we've used in this class for some of the more complicated examples.